not bound to its activator site. It's not regulating this gene. And you have no. All right, so that's the dichotomy between the positive and the negative and negative and the positive. Let's just step through these 4 panels now. All right, so let's imagine a scenario where I have lactose available but no glucose. So just logically think it through right now. If I have lactose available but no glucose, I'm a cell, I want to divide, I want to grow, I'm going to break down the lactose. Okay? So, and so you need those genes. I need the enzymes to break down the genes. So in that case, lactose is available but no glucose. Lactose is available, allolactose binds to the repressor, pulls the repressor off the gene. No negative regulation there. Got that going for you. But also, we have no glucose available, so the cap is now active. So you have negative regulation removed and positive regulation added. And obviously, transcription occurs. We're going to make all the genes negative now. All right. In an alternate scenario, you have lactose available and glucose. All right. Lactose is available, so you have allolactose bound to the repressor, so the repressor is off of the operator. So you have nothing repressing. You have no negative control. Okay? But because glucose is available, cap is now inactive. The inducer is inactive. It's not bound to that positive site, that activator site, the cap site. And so you get no transcription. So remember on a couple of slides ago I said you need positive regulation for this to happen. If you want to call, I don't know how you play cards, it's like it trumps. So cap trumps. Now, even though the repressor is off, the fact that cap is not attached actually trumps, and you don't get the transcription. All right. So if neither glucose or lactose are available, you have no lactose there, no allolactose, so the repressor is bound to the operator. This is nice and easy. The repressor is bound to the operator because you have no lactose. But because you have no glucose, cap is bound to that positive site, that activator site. But in this case, because the repressor is downstream, you still don't get transcription. Okay, and think through it logically. If I have no glucose, no lactose, doesn't matter. I'm not doing anything. I'm just sitting there waiting for something to happen. All right, and now in the last scenario, you have glucose available but no lactose. So glucose is available, therefore cap is inactive. So you have no positive regulation on this gene, plus you have negative regulation on it. Because you have no lactose, the repressor is bound to the operator. So in this case, you have glucose available but no lactose, so this organism is going to metabolize that glucose. Okay? In this case, he's got neither glucose or lactose available, so he's not metabolizing anything. He's just hanging out. Stationary phase, whatever. In this case, they have lactose and glucose available. But I'm not transcribing anything. Why? This cap's not on. And why else, Priya?
That's how she said cap is
Cap's
not
not on. But just make it logical for me. You're both absolutely correct. Cap's not on, so I'm not going to transcribe anything. But you have glucose. Yeah, so why am I going to bother to degrade lactose? All right, and here we have lactose but no glucose. So that's why we definitely need this thing on. Let's make a transcript. Let's make some enzymes. Let's degrade lactose. All right, you guys comfortable? Everyone lost? Yeah.
So you need lactose to make negative control?
No. You need, good question, how can I answer this clearly? It's not that you need lactose, it's that when you have lactose, when you have lactose and no glucose, you're under positive control. You're under negative control when you have no lactose. Because, it's good to make you talk through it different ways. Because the repressor binds when you have no lactose. So that makes it under negative control. Hopefully that helps a little bit. And this is tricky. Let it soak in for a day. It's tricky. People get hung up on this. where we have both lactose and glucose available, and some of you, many of you have gotten very quickly comfortable with the idea that I'm going to degrade glucose first. So in this case, we have lactose and glucose available, that operon is not turned on, this organism is degrading glucose. But eventually it's going to use all that glucose. Okay? And so if we look at, if this hopefully looks to some degree familiar to you as a standard growth curve for bacteria, you're right, it's just in two phases. So here you have time across the x-axis, and you have bacterial density, the total cell numbers there across the y-axis. And remember, you have a lag phase, so there's a lagging growth. Okay, it's adjusting to the fact that, oh, look at all this glucose, I'm going to start growing and dividing, I need to make glycan, I need to do all this stuff, I need to replicate my chromosomes. All right, and then the glucose gets used, and they're growing like crazy, growing exponentially while the glucose is being used. At some point, the glucose is used up, and this you can see really nicely in the test tube. Obviously, in the environment, it's not hard to see, but in the test tube, you could do this really easily in the lab. So, glucose gets all used up, and we go into stationary phase, right? But in this environment, they also have lactose available. So because they have lactose available, what this stationary phase is really another lag phase. Another lag phase for what? What is happening in that lag phase? Yeah, start making the enzymes necessary. So this is what's happening in that lag phase. You're switching on the genes, you're turning on that operator so that transcription can occur. Okay? And then they use lactose. And it's just a way of understanding that they're going to grow in phases depending on what's preferential. It's also a way of understanding in a very practical sense why we have, or we don't have it, some degree, why bacterial cells have gene regulation at this level, at the operon level, to control for what they're degrading when. All right, so this is catabolic operon. Catabolic operon. Okay? Let's switch over to a biosynthetic operon. And now anabolic operon. Biosynthetic. So in this case, we're dealing with cells wanting to make tryptophan. Okay, so on the cell I'm dividing, I have plenty of lactose and glucose available, I've got loads of food, I'm going to start dividing, I need to make proteins, I need to make glycan, I need to make more DNA, etc. Okay, so that cell needs to make tryptophan. To make tryptophan, you have a series of enzymes that make the tryptophan, and this operon looks very much the same. Okay, you have a promoter, and you have an operator region. You have a regulatory gene that is upstream. It's going to make a repressor. Upstream, promoter, operator, and then the genes. Okay? And don't worry, for the purposes of this class and this exam, don't go into the attenuation of this. I've done it in other classes and it just never works. So you don't have to worry about the attenuation of the triple operon if you're reading the textbook. All right, point being, in this case, they have low tryptophan levels. This cell wants to divide, but its tryptophan levels are very, very low. So it needs to make that. It needs to make, I want to make a bunch of cars, but I don't have enough engines. I need to make all the hardware, buy all the nuts and bolts and the steel to make more engines. Okay? So what it's going to do is, in that case, this is a negatively regulated inducible gene. So in this case, the repressor is going to be removed from the operator site, allowing RNA polymerase to bind and transcription to occur. Alright? And that's because tryptophan levels are low. I need to make more tryptophan. Okay? But what about when tryptophan levels are high? Going back to the last test in your last series of slides before that class, that first test, talking about feedback inhibition of enzymes. This is a classic case of feedback inhibition, where in this case, we have tryptophan levels are now high. I don't need to make any more tryptophan. Plenty of cars on the lot. I don't need to make any more. So what happens then is tryptophan itself comes back and binds to that repressor. When tryptophan is bound to that repressor, it's a co-repressor. We're under negative regulation, so it binds up to the operator and no transcription occurs. So this is classic enzyme feedback inhibition with a let's think about some other layers though of gene regulation. So what we're talking about so far is just the purest sense, am I gonna transcribe a gene or not? Am I gonna turn that operon on or not? There's also ways to attenuate that. Attenuate in terms of not just turn it on or off, but use the dimmer switch. Turn it on or off just a little bit. Slow it down. Okay? So I'm cranking this out, I've got an anabolic gene, a biosynthetic gene, I'm cranking out the enzymes necessary to make tryptophan, but I'm starting to have more and more tryptophan, maybe I wanna slow that down. So one way to do that is with ribose switches. So here, in this case, you don't even need to know the details of it, I don't remember the exact details of it. You have a messenger RNA that has some sort of three-dimensional structure. Okay, and the point of this is to make riboflavin. Okay. So if I have plenty of riboflavin available in biosynthetic capacity, I'm trying to biosynthesize that, and I have plenty of it available, you can take a metabolite of that riboflavin and actually reshape the messenger as it comes off such that it will no longer transcribe. So you can stop transcription, not just before it starts, but you can stop transcription midway through the process. Alright, so here you have a messenger, it's coming off, okay, coming off of the RNA polymerase. At some point you start having it all the while downstream, that messenger is being translated also into the enzymes necessary for that, for this protein. Alright, ends up making riboflavin. Once you have plenty of riboflavin available, a metabolite of that can come back and actually turn off transcription midstream. Slow it down. It's just a way of slowing things down without necessarily turning them completely off. Alright, and you can do the same thing at the translational level. So here you have a messenger going through the ribosome. And then you can have feedback. In this case, they just call it a ligand. You have some sort of feedback from the outcome, negative feedback coming back from the products of that biosynthetic pathway that will come back, alter the morphology of your messenger such that translation stops and you don't make any more of that protein. So you can have regulation at the gene level and an on-off level by turning operons on and off. But you can also have regulation that slows things down at the transcriptional level by messing with the shape of the messenger, and at the translational level, messing with the shape of the messenger as it moves through the ribosome. Alright, okay, quickly I'll go through global regulatory stuff, but before I do, does anyone have a question? Alright, okay, global regulation. So what we've been talking about for the last 45 minutes are very specific gene regulation. I want to control the gene to make beta-galactosidase, the enzyme that breaks down lactose. I want to control the gene, makes the enzyme to make tryptophan, etc. Very specific. But you can have global regulators. And one of the most famous global regulators there is are sigma factors. These are sigma factors. Okay. So it's a regulatory system that controls a whole suite of pathways. It controls an entire process, not just the breakdown of one sugar, lactose. It controls a whole entire process. And sigma factors are really famous for that, and there's a lot of different sigma factors. For example, stationary phase. I told you guys when cells go into stationary phase, they'll completely shift their gene expression. They'll shift their gene expression from things like metabolism, breaking down catabolic processes and anabolic processes, to ways to survive stress and starvation or possibly low oxygen, etc. They completely change the genes that they have turned on and turned off in association with now I'm in survival mode, as opposed to before when I was just in metabolic active mode and divided. They're going to need a very different set of genes turned on, and the sigma factor regulates that. And remember, we also said sigma factors, and it makes sense. Sigma factors guide the RNA polymerase down to that promoter site. So they physically help decide where the RNA polymerase goes to transcribe. All right, I'm also going to talk to you about quorum sensing. Quorum sensing is this amazingly cool thing that cells do to communicate. whole lot of this one chemical that I'll show you in just a second. That one chemical, not only does it communicate from cell to cell and across species lines, but it also turns on other genes. It turns on a whole slew of genes. And then last, I'm only going to just show you one quick slide, sporulation in bacillus. Bacillus is, sporulation of bacillus is controlled by global regulation. It's basically a starvation response for that particular genus of organism. Clostridium is it too. And that's run by sigma factors. So that's more of an example of this. Okay, so these sigma factors, there's a lot of them. And this is just for E. coli, and it's just a couple of them. There's a lot of sigma factors. But you can have, as I said, it globally regulates big processes, such as all the genes needed during exponential growth. So when they're going through exponential growth, they're dividing rapidly, they're metabolizing tons of peptidoglycan, replicating their DNA, etc. And they need a certain set of genes for that. They need all the replication genes for DNA replication. They need the proteins necessary for peptidoglycan synthesis, bacterial, polylysins, all of those things, UDPs, etc. Everything you learned for that. So all those genes get turned on, and they're all regulated by one particular sigma factor, sigma 70. All right. Likewise, when they go into stationary phase, sigma S, they need a completely different sigma factor. That sigma factor regulates all the genes necessary for stationary phase. And you can go on. You can have nitrogen metabolism, etc., membrane proteins, etc. So big processes. Assembly of a flagella. So a big process is going to get controlled by one main contractor. And that one main contractor is a sigma factor. So let's talk quickly about quorum sensing. So quorum sensing is a really cool microbial thing that we've only known about really in the last 20 years. And it's cell-to-cell communication. And the chemical in question is NaCl-homoserolactone. And this is a chemical that cells will excrete out into the environment when they're in very high density. So we call this something that is under density-dependent regulation. So when you have more and more cells in the environment, you have more and more production of this AHL, homoserolactone. All right, and it feeds back on itself. So if I'm producing, the cells are getting more and more dense, they start producing more and more AHL, and that triggers other cells to produce more and more AHL. So it's a positive feedback loop. It's going to continually positive feedback where you end up with more and more of these chemicals. All right, and so they use that as a really important communication tool, letting themselves know that, hey, we're going to use chemicals back. It's important in biofilm formation, obviously. When cells are all piled up too dense in the biofilm, start releasing these chemicals, and that will trigger others to slough off from the biofilm if the environment's getting too crowded. It's also important in functioning like light generation. So, who's ever heard of any of these glowing fish down in the deep part of the ocean? Or have you seen them in some videos? I took videos of them in my college class. These glowing fish, and bacteria do it too, are glowing because they have symbiotic microorganisms of Vibrio species, Vibrio fischeri, in an organ. And they're in such high density, the microbes are in such high density, when they get in high density, they turn on their quorum sensing, they turn on AHL, and that triggers production of a lux gene that allows those cells to glow. So the glowing in these glowing deep sea fish is actually just really dense communities of microorganisms living in symbiosis with that fish. So this is a really nice kind of fun application of this, where they're actually benefiting by doing this glowing because it makes them useful to fish in a really habitat and environment. And then the book has a really cool cartoon, but what this is just showing, you do not need to memorize this in any way, shape, or form, but what it's showing is that as cell density increases, they produce more and more and more of the AHLs, indicated by these red dots. Homoserolactone chemical. Increasing the presence of that chemical turns on, it works as a global regulator because it turns on other genes. So in the case of these light fish, as microbes living within this light fish, it's turning on the lux gene. luciferase for the light, for the light pink. And it's actually turned on by this global regulator, which is acetylhomocysteine lactose, which is a chemical. Alright. Okay, and then the last thing is just go through the fact that sporulation in bacillus is driven by a sigma factor. I should move this up with the sigma factor slide. And it's a series of sigma factors. So as the cell gets into more and more starved conditions in a more and more stressful environment, those sigma factors will get upregulated, and then they will control further the genes necessary to completely reshape the cell and form that internal spore. And it's controlled through a series of sigma factors. Alright. Okay. Questions? Yeah.
The sigma factors the genes that are kind of turn on at once.
I'm really glad you asked that. No, a sigma factor in itself is actually its own protein. It's its own protein. Its gene may be nearby, but not necessarily. So it's its own protein. And the sigma factor, remember, so it's this protein that's out in the environment. I'll give you an example in just a second. Actually, it didn't matter because it would be a protein out in the environment, and that protein, when the conditions are right, say that cell wants to make a gel or whatever in the stationary phase, it will guide the RNA polymerase to the correct piece. So think about it almost like a chaperone. And it knows, okay, it knows, oh, the building's on fire, we need to get everybody to this location. Crappy analogy. Alright, so let me tell you a better analogy this Sunday. So my master's work was looking at biofilm formation, but looking at sigma factor control of biofilm formation. And so what I did is I had knockouts, E. coli, that were knocked out for the gene for the sigma S, or POS, it's the new thing. So I had cells that were knocked out in that gene, and those cells could not survive stationary phase as well as cells that did not have that sigma S, okay? Because they didn't have this chaperone protein controlling, globally regulating all the genes for stationary phase. So in my case, they didn't form biofilm. They're much more potent. So anyway, the point being is that it's just a protein that is kind of another cheesy analogy is the contractor in charge of getting all these other things done. Making sure that all those other genes get expressed. And if you remove that, like in my case, I removed sigma S from those cells, they didn't function. Population levels went down, they didn't adhere, they didn't adhere well, and the biofilm. Yeah. Alright, anyone else? Okay, you guys have a good week. I will see you next Thursday.